Hello, everyone. I'm Boyang Wang, a master's student in the Electrical Engineering and Computer Science Department at the University of Michigan. Today, I'm excited to share our latest research project with you, VCISR, Blind Single Image Super Resolution with Video Compression Synthetic Data. This work represents a significant leap forward in the realm of image enhancement, specifically tackling the challenges of single-image super resolution in the context of video compression. Let's dive into the details of our innovative approach and the impact it holds for advancing the field. As an overview, we present a video compression-based degradation model to synthesize low-resolution image data in the blind SSR task. The proposed method achieves better results in restoring generic image quality degradations. The proposed network can super-resolve images with the ability to restore video compression degradations as well. Talking about other contributions, we propose a testing dataset that focuses on restoring video compression distortions. The proposed approach achieves superior performance in SOTA no-reference quality assessment on both image super-resolution datasets and video super-resolution datasets, and shows better visual quality. To begin, let's explore why super-resolution matters. First, it's about restoring image quality and tackling issues like noise and blurriness. Second, it enables higher quality with less bandwidth, optimizing data transmission. Lastly, it contributes to an improved streaming experience, ensuring a seamless and visually pleasing interaction. Moving on to our goals. Our first aim is to restore image-level unknown degradations, adapting to diverse, unknown challenges in real-world scenarios. Additionally, we focus on addressing compression-induced distortions, especially in the temporal domain. Our goal is to navigate and rectify these challenges for high-quality image and video reconstruction. In aligning with these fundamental needs, our research pushes the boundaries of image super-resolution, contributing to enhanced visual experiences and efficient data utilization. Before we dive into our groundbreaking work, let's take a moment to understand the general pipeline in image degradation, building upon previous research. First is the general degradation pipeline. The foundation of image degradation involves four main sources: blur, noise, resize, and JPEG compression. Over time, this pipeline evolved. Researchers enhanced it by incorporating a second-order model, elevating the simulation to better capture the intricate and complicated degradation patterns within an image. Next, I want to talk about the motivation of our work. We noticed that many previous approaches encountered challenges when it came to addressing degradations caused by video compression, especially when dealing with a single video frame as input. Common issues include mosquito noise, ringing, blockiness, and staircase noise artifacts. Inspired by this crucial observation, we took a groundbreaking step. For the first time, we introduce a video compression-based degradation model aimed at synthesizing low-resolution image data. This innovative approach allows us to tackle the unique complexities introduced by video compression, setting our work apart in the realm of image super-resolution. Drawing wisdom from the high-order degradation model, we propose a degradation pipeline to synthesize video compression artifacts with image datasets. Thus, a single degraded image can contain distortions caused by the lossy video compression algorithms. This pipeline could also overcome the leak of feature diversity in video data and thus retain the training efficiency. In the data preparation stage, we first crop images into small patches and process them in normal degradation order. After that, we apply video compression to the distorted batches. To model real-world compression artifacts, we incorporate a rich collection of compression models. Firstly, we employ diverse video compression standards, MPEG-2, MPEG-4, H.264, and H.265. Secondly, various quantization parameter control is considered, including constant rate factor, CRF, and bitrate control. Lastly, we allow for variable encoder speed control, such as preset settings, slow, medium, fast. The SR network trained with our proposed data synthesis and degradation block can produce finer details and more visually appealing results. Our method can restore texture without introducing ringing artifacts and unfaithful reconstructions. It also demonstrates an even better ability to resolve blurry artifacts compared to the VSR method under high-motion scenes. Need to mention that, as for the anime content, the HR images super-resolved by VCISR have much less block artifacts and fringes. The proposed method exhibits similar or better quantitative results on the tested data for ISR and VSR tasks compared to recently published works with much fewer network parameters. The result showcases that involving a video-based degradation module can produce effective restorations even without leveraging the temporal correlations by referring to previous frames. Thank you for watching this video.